Yeah, like a screen thing. So we just looked at what was effectively the secant theorem. Okay, we talked about how these two overlapping and similar triangles gave us proportional sides, which could then be rearranged to show that literally the outside of a secant times the whole of a secant equals the outside of another secant times the whole of the other secant. I'm seeing all the nods. Good. So now I want to look at number 3. Okay. So we're considering a circle. We got a circle here with point P outside. Draw a line through P that intersects the circle in chord AB. So we got that. Okay. And draw the chords AT. And a line that is tangent to the circle and passing through P, but it's tangent to the circle at point T. Griffin, question.
I don't know if this is important, but would you have to extend that? Do you have to extend the tangent, or can it just land on point T and not go on?
Can just land. I mean, it's fine.
Okay, yeah, I know.
Yeah. No, it's fine right there. But you're right. Technically, it could be. Interesting. It could be extended. Okay, so we've got a diagram that looks like this, correct? And we're trying to prove the triangle PAT, right? We're trying to prove the triangle PAT, and PTB are similar, correct? So far, so good? Yeah. Okay. So I'm going to find this incredibly useful to draw these two triangles separately. Okay, so maybe I'll do this one here. So that's PTB. That's PTB. Cesar, thought?
I was saying that I was playing this thing. He was asking really to draw these up with his helpful, and I said, yeah, but it's kind of hard for me to see them as being similar.
Right. As Cesar points out, it's hard to see them as similar, kind of when they're overlapping here. But and interestingly, also when they're like flipped upside down.
It seems like you would want to prove the sides or the angles are similar, and then separate them so that you like know that they're similar, and then you can like manipulate them to what you need.
Also a great point, right? Maybe it's helpful actually to just work up here first on this diagram, and then show it in two separate triangles. Either way, I'm just going to show it separately here. So this would be P, this would be T, and this would be A. Okay, so before we used similar triangles, which we found using angles. So I'm curious, does anybody have a thought on, I don't know. Josh, how did you approach this problem?
Angle intersects arc BT.
Interesting. So Josh is saying that angle BAT intercepts arc BT. Okay.
And then we see that angle PTB intercepts the same arc.
Angle PTB intercepts the same arc. Wait, sorry?
They're the same.
Oh no, it's not tangent.
No, because this is not tangent, right? Okay, so indeed, Josh, that is huge, saying that angle PTB is equal to angle PAT. Okay? So that's one pair of equal angles. Devin, do we know of any others?
Well, I don't know the equal angles exactly, but on triangle ATP, the T is 90 degrees.
That would be the case if that line went through the center.
Yeah.
Okay. Any other information that we have here on other angles? Simon?
Well, there's another pair of equal angles, so I just extended the segment from like the PT, the tangent thing, like farther to the left, and then
This?
yeah. And then, I just like made some arbitrary point called J. I only need it for the sake of the angle because like can I come up?
Yeah.
Because this is like
the tangent inscribed angle. Why is the triangle orange?
Because it's
Oh
orange.
yeah, because it's orange. So like this, that's very bad. It intercepts this arc, and then so does abt
Nice.
cap TBA.
Nice. So that shows that that's cool, Simon. So that shows that these two angles are equal, which because to any straight angle adds up to 180, in turn shows that those two angles are equal, right? Isn't that right? I mean that's why those angles are useful, because added to this angle right here added to that angle has to equal 180. Same is true up here. Therefore, those two angles are equal. So you can show that these two angles are equal. Was there any maybe more obvious angle that was like equal to itself? Here, Sam.
Angle P.
Right, angle P is equal to angle P. Correct?
And then
Right?
share.
So regardless, now we've really done it. We've got all three sets of angles equal. So what do we know about these two triangles?
They're similar.
Similar by why, Carlo? Right? But by what? Why are they similar?
Because their angles
Or what? The angles are equal.
Congruent.
Yeah.
All three angles are equal. All three angles are congruent. So we could say because of all three angles being equal or congruent, we can say these triangles are similar. Triangles similar by angle, angle, angle. Okay, right? Is that right? Okay, we're laughing because
You're turning frantically.
I'm turning frankly. Okay, yeah, okay, I'll take that. That's good. At least I know we're awake. Okay, so we've proven the two triangles similar, and our goal is eventually to prove that PT is it squared? PT squared? What are we trying to prove here, Michael?
P squared.
PT squared equals PA times PB.
Equals PA times PB. So any idea using what we just maybe this is a similar problem to an earlier one. How could we conclude this? Lexi, yeah.
Well, you could basically set up another proportion.
Lexi says set up a proportion. Go on.
And if you could set up PA over PT because they're corresponding sides.
I love it. PA over PT.
Since you know they both have the angle, like the one angle and the other one, over, and then equals PT over PB.
Equals PT
over P.
over PB.
Because those are also corresponding. Wait, yeah, PT over PB.
Because those are corresponding sides. They're between the same two angles. It was perfect.
And then you can just cross multiply.
And then you can cross multiply, right? We know that similar triangles have proportional sides. We can cross multiply. So we get PA times PB equals PT times PT.
Can you draw like a general? Like the rule of
Well, yeah, so if we look to compare it to the first one, right, we just have, or sort of make it similar to the first. Instead of having two secants, you've got a secant and a tangent, correct? And again, we've got the outside, right, of a secant. The outside of a secant times what?
The whole thing.
The whole thing. Not a trick question. The whole thing. Outside times the whole.
Times the outside, which is also the whole.
In a way, times the outside, which is also the whole, right? It's like you know, just the whole tangent in a way, just like the whole tangent times the whole tangent, right? But I like the way Sam put it. He related it back to this, right? Where it was outside times the whole equals outside times the whole. Now it's like the outside and the whole are like the same. right? That's another way of thinking about it, right? So the outside times the whole is equal just to the whole tangent squared. Question?
Yeah, I don't know. We're just kind of confused because the two similar triangles, it's kind of fun that. The two similar triangles like have T, like both have T, so then we just got confused.
Right, they both have T. I agree. It's hard. These overlapping triangles is very tricky.
Yeah.
Right? And especially because like angle T in one of them corresponds to angle A in the other, and angle T in another one corresponds to angle B in the other, right? So I agree, it's hard. That's why I really suggest you've got to draw them separately and work in concert with this other circle, with the other diagram. Okay? Questions? Now's a great time for questions. Lexi.
Does it matter if the tangent extends? Like, the point of the tangent?
Well, let's see. So we've got this. If we extend the tangent, Griffin asked the same question earlier. We extend the tangent, does it change anything if we were to, redo the problem? Would it change anything about?
It makes it a little easier. Because
Maybe it makes it easier to see, but does it change our outcome?
Like the theorem still applies.
Yeah, it would, I think, right? Because you would just redo this whole similar triangle thing. Yeah. Okay. Other questions? All right. Someone might be saying, hey, what's the point? Well, let's do an example problem here and find out.